Hi, everybody. We are back in this segment. We're going to talk a little bit about the properties of estimators and what they're trying to estimate, as well as something known as the sampling distribution for some sample data. And we're going to take a look at a pretty interesting result, I think, in the next segment known as the central limit theorem, which suggests that even though populations may not be normally distributed, the assumption of a normal distribution when we're talking about the sample mean distribution is actually a fairly reasonable one. So let's go ahead here and just kind of remember, what our goal is in conducting statistics. And in general, what we're trying to do here is to make inferences about a population based on a sample, right? For example, in this slide here, the population parameter mu, we don't know what that is, but X bar is our best guess at that. X bar is an estimator of mu. Similarly, S, our sample standard deviation, is an estimator of sigma, the actual population standard deviation, again, which we may not know because of the complexities of trying to sample an entire population. So let's start out here just talking about a statistic. Okay, a statistic is a type of random variable in some sense because the actual values of a statistic are generated from a sample. And if those samples are being randomly collected from a population, the sample statistics themselves will differ from sample to sample, meaning the statistics we can think of as random variables. So depending on the sample size, the statistic could either represent the true population value pretty well, right, if we have some representative sampling going on here, or it could differ greatly if the sample is not a good representation of the underlying population. So what we're going to do here is we're going to take a look at 8 random samples of size 5 from a larger population. And the population we're going to be interested in here is the population of GMAT takers. So these are, again, potential MBA applicants here. And in any given year, there's about 250,000 individuals that take the GMAT through the GMAC. And we're going to go ahead and look at some sample data rather than looking at that entire population here. We're going to just draw randomly samples of size 5. And you'll note for each row that we're looking at here, or each column rather, represents a different sample. So we have 8 different samples. Each sample has 5 different individuals chosen. And you'll notice along the bottom row here, we have computed the sample mean for each of those 5 samples. Okay. And you'll note that the sample means are not all the same. They vary a little bit, and this is what we mean by a sample statistic being a random variable. There's a little bit of noise in every sample. Okay, every sample is randomly taken, so every sample is a little bit different. And because of that, we can treat the sample statistic, in this particular case, the sample mean, as a random variable itself. Now, if you were to take the average of these sample means, okay, it turns out the average of these is 536 1/4, and this is fairly close to the actual average GMAT score of 520. But there is definitely considerable variation between samples, and that's something we're going to go ahead and think more about. So let's go ahead and think about conducting kind of an interesting experiment here. Normally, we don't really consider knowing the full population, right, which is why we are taking samples. Looking at the full population is often too costly, very complicated. But what we're going to do in a moment is we're going to look at a whole population that we actually know. It's going to be pretty small. And we're going to go ahead and think about the process of generating all of the possible samples. In this diagram here, we're only looking at 8 possible samples of 5 scores. But imagine if we looked at every combination of 5 score samples that we could have drawn from those, somewhere in the neighborhood of 250,000 possible elements of that population. Okay, so we're going to think about that experiment in a moment here when we generate what's known as the sampling distribution. Now, just a little bit of terminology here. An estimator is a type of statistic derived from a sample in an attempt to try to make our best guess about what the true value is of a population parameter. Okay, the estimate is a particular value of the estimator, okay, which again is going to depend on the sample data that was drawn. So for a particular estimator, you may get many different estimates as you look at different samples. The sampling distribution we're going to think about here is the probability distribution of all possible values the statistic of interest might assume when we are taking a random sample of arbitrary size. Okay, so what we're going to do here is we're going to think about measuring every possible sample from a population, okay, and then measuring them by, like, let's say the sample mean here. And those measurements would create a sampling distribution for that sample mean, okay, such that the average of all the sample means would be equal to the population mean. Okay, so let's go ahead here and take a look at an example of developing a sample distribution. And this hopefully will motivate what we're going to do in the next segment. So let's suppose there's a population of size 4, right? If it's only size 4, why not sample the whole thing? You're right, we could in this particular case, but in most cases, the population is too large. We're going to take a look at this particular example because I think it illustrates a very important point we're going to come back to later, which is the central limit theorem, that even though population data may not be normally distributed, the sample means actually tend to be, provided an important condition is met regarding sample size. So let's suppose our random variable x in this experiment is the age of individuals, and we have 4 individuals here you might recognize in our population, and we'll just call them individuals A, B, C, and D, whose respective ages at the time they were sampled were 18, 20, 22, and 24 years of age. Okay, so here is our population. And we could think about now, given this data here, right, given our sample data, we could go ahead and compute some summary measures, or sorry, not given the sample data, but this is technically population data here, right? These are our 4 individuals. We're going to think about in a moment of creating samples, subsets from this group of 4, but we know the population data in this example, right? We know what their ages are, and we can go ahead and generate some population statistics that summarize our distribution here. For example, we can compute the population mean here by adding up those 4 ages, dividing by 4, and we see on average they are 21 years old. Okay, we can also compute the population standard deviation here, which comes out to about 2.25-ish, okay, years. Note that in our sample, we only had 1 individual in each of these 4 classes, so our population distribution, it does not look like a bell-shaped curve here. In fact, it looks like a uniform distribution. It's very flat. The likelihood we would sample randomly any one of those individuals is the same at 25%, right? There's only 4 of them, so if I randomly pick one of them, they have a 25% chance of being sampled. Now, what we're going to think about is kind of a strange experiment, but you will see the point of this momentarily, is we're going to consider here all possible samples that we could generate of size n equals 2. Okay, so we have these 4 individuals. We're going to put them in a bag. We're going to shake that bag up. We're going to draw one out, measure their age, put them back in, and draw another one out to give us a sample of 2. Meaning it is possible for us to sample the same individual 2 times. This can happen. Okay, and we're going to go ahead and keep track of our results here in a table. Let me go ahead and clear that off there. So if we were to sample the 18-year-old, which is individual A, if we sampled them 2 times, then our sample, where the first observation is 18 and the second observation is 18 years of age, would look like this. And we're going to go ahead and just go across that first row. So what happens if first we sample the 18-year-old and then we randomly get the 20-year-old? That's again a sample of 2. but we didn't resample the same individual twice. There we got two different people, an 18-year-old and a 20-year-old. Okay, and then in this third cell here, we're sampling the 18-year-old and the 22-year-old and the 18-year-old and the 24-year-old. Okay, now you'll note here we sampled the 18-year-old first and then the 20-year-old, but we could have sampled the 20-year-old first and then the 18-year-old. Okay, in this cell, this corresponds to us sampling the 20-year-old twice, right? And I think hopefully you get the point here, but we can think about all possible two-person samples that we could draw here by resampling from that population over and over and over again. And hopefully you see that is 16 possible samples that we could generate. What we're going to do now is for every one of those cells, we're going to look at the two observations in the cell. We're going to calculate the sample mean, and we're going to move those sample means onto this new table. Okay, for example, in this first cell here, where we have both 18-year-olds, if we take the average of 18 and 18, then in this cell over here, we should get 18, right? That's the average of 18 and 18. Similarly, if we go to the second cell and we see what's that? Well, this is the sample where we have the 18-year-old and the 20-year-old. Now, if we measure their average age and we put that here, the average of 18 and 20 is 19. And note we didn't have a 19-year-old in our sample. Okay, we did not have a 19-year-old in there, but the sample means will have an element where you can have 19 years of age as a possibility. Okay, we can do it one more time. Move over to the third cell here, taking the average of the 18 and 22-year-old's age, which in this cell becomes, good, 20. All right, and we can keep doing this. We'll do this for every single cell, which means, again, we're going to wind up here with 16 different sample means. Now, you'll notice not all of the sample means occur in equal frequency, right? Which is kind of weird because we know in the population, each of those individuals, A, B, C, and D, occurred with equal frequency. Each one occurred 25% of the time. They each represented a fourth of the population. But if you look very carefully across our sample means, okay, you'll notice there's one value that shows up way more frequently than the others, and that is 21. 21 shows up 4 times. However, we see that there are some values that only show up 3, right? 20 shows up 3 times. Right? So does 22. Similarly, 23 and 19 each only show up twice. And 18 and 24, those only occur once. Those are super rare because those involved us sampling the extreme observations repeatedly, right? We sampled the 18-year-old twice, we sampled the 24-year-old twice. That was the only way we can get a sample mean of 18 or a sample mean of 24, given our population here. So let's go ahead and we're going to now take this table that we've constructed and we are going to create a frequency distribution table to think about plotting a bar chart or a bar histogram for this discrete data here that we're looking at. Okay, so 16 sample means, right? And they had these possible set of values here, 18, 19, 20, 21, 22, 23, and 24. And we recognized some of these values occurred more frequently than others, right? For example, 18 only showed up once, 19 showed up twice, 20 was one of those culprits that showed up 3 times, and 21 was the most commonly occurring sample mean here, which showed up 4 times, and then the count goes down. What does that mean for this picture in the right-hand diagram here? Well, what that means is if we wanted to plot the distribution of X bar here, let's plot a histogram measuring this frequency table that we've just calculated. Okay, you'll note that this distribution does not look like the population distribution, right? The 18-year-old only occurs 1 out of 16 times in that distribution. Okay, the 19-year-old, 1/8 of the time. 20-year-old, 3 out of 16. 21-year-old mean, okay, occurs 4 out of those 16 samples. Probability 0.25. Okay, so here is the important thing to see, I think, from this experiment. Okay, when we look at the underlying population was flat, right? The average age was 21. Note the sampling distribution on the right here also exhibits the same mean. All right, and that's an important property we're going to talk about in a moment here, that the means of the sampling distribution and the population distribution, they will always be the same, because the sample mean turns out to be what we call an unbiased estimator. So we're looking right at the target that we're trying to shoot at, which is the population mean. Sometimes we're a little off, but at least we're looking in the right spot. Hey, what is different? Well, the standard deviation of the population is a little bit different than the standard deviation of the sampling distribution, of the sample means. Okay, and we're actually going to show an analytical result later that the standard deviation under that sampling distribution always has to be smaller than the standard deviation underneath that population distribution, at least if you have more than one element in your sample set. So this picture that we're looking at here, this is an important picture. The left diagram is the underlying population, okay, which is flat, doesn't look normal at all. But the right diagram, the distribution of the sample means from that population, from all possible samples that we've generated, that tends to be normal. Okay, which means the assumption of a normal distribution turns out to apply in quite a large number of situations. Okay, which is why we spend so much time studying that normal distribution. They are everywhere. All right, moving along. So here's the idea. We had some normal population distribution, or actually, we actually didn't even have a normal population distribution in that last example, but we'll see this is still the case, even if the population was normal. Okay, the sampling distribution will also be normal, and they will both be centered at the same place. The mean of the sampling distribution will equal the mean of the underlying population distribution, which we saw happen in that last example with our 4 individuals, A, B, C, D. Okay, now what's going on here? Why do we need a sampling distribution? Well, remember that sample statistic, the sample mean X bar, that is a random variable. And this green picture in the bottom here, okay, that is showing us in some regard the randomness in our random variable. We're able to model that, and what we're modeling here is an idea, again, known as sample error, okay, or sampling error. And this is the small differences between the mean of a particular sample relative to the population mean. Okay, and the sampling error could be positive, could be negative, depending on if the sample mean was smaller or larger than that population mean. And the average sampling error, this goes down as we increase the sample size. Okay, the average sampling error goes down as we increase that sample size. And an important property of an estimator that we typically want, it's a desirable property of an estimator, is a property known as unbiasedness. Okay, and if an estimator's value on average is equal to the population parameter that is trying to estimate, which means on average, we're looking at the center of our bullseye, right? Our estimator is like, we're throwing darts at a bullseye, and the estimator is a dart. Okay, and because of sampling error, we're maybe a little bit near the target every once in a while, but we might not hit it always exactly, but we're at least looking at the right spot. Okay, so if you have an unbiased estimator here, the average value of that estimator will equal the true value in the population. If the sample mean X bar was not unbiased, meaning it was a biased estimator, then what that means is we're not looking at the center of the target anymore. Okay? This is a situation where the expected value of X is no longer equal to the population mean. So in this particular drawing, the expected value of the sample mean is overshooting mu. Okay, so the bias here is the difference between the expected value of the estimator and the true parameter. A little bit different than just a single sampling error. This is the average sampling error across all samples. Okay, so we're saying on average, an unbiased estimator should not be overstating or understating the true parameter value under the population. So these two things are a little bit different, right? The sampling error occurs when our sample, even if properly drawn, is not a perfect representation of the population. That's why one particular sample mean could be different than the population mean. But the bias, okay, bias is systematic. Okay, sampling error, this is random. Okay, but bias tends to be systematic, and an unbiased estimator avoids systematic errors. Okay, sampling error, this is not really the researcher's fault, right? Every sample is a little bit different because they're not a full reflection of the underlying population. Bias, as it turns out, tends to be more a practitioner error that could be corrected often very easily. If you know you're overshooting, you're over-predicting, okay, then what do? Well, when you make your prediction, you bring it down a little bit. So once you identify that bias, you can adjust for it. But again, when we're thinking about biased and unbiased estimators, I like to use this analogy of us shooting at a bullseye here. And in this question here, if the center of the bullseye represents the parameter being estimated, then in which figure is the estimator unbiased? The answer is the left. Okay, note that in both figures, there is a little bit of spread. Right? There's a little bit of spread in how we're shooting. So it's like we're shooting at the target and our hand is a little shaky. That shakiness is the sample error. Okay, but where are we looking? In the left diagram, we're actually looking at the middle of the bullseye. But in the right diagram, you can tell our aim is a little too far over to the right. So if you recognize your aim is too far over to the right, how do you fix that? You adjust a little bit to the left. You have identified the bias and you can correct it. So left unbiased estimator in terms of this analogy, and the right diagram is a bias estimator. Now, another important property of an estimator that we're going to be interested in is something known as the efficiency of that estimator. And the variance of an estimator's sampling distribution is related to the efficiency criteria here. So a more efficient estimator has a smaller spread or a smaller dispersion. Okay, in the context of our target, our bullseye here, we can think about, again, a more efficient estimator here. Our guesses are very tightly woven around that bullseye. Notice the less efficient estimator, it's not biased. We're still looking at the middle here, but there's more of a spread, so it's less efficient. In both cases in this picture, though, both of those estimators in the context of our analogy are unbiased. We're looking at the center of the bullseye in both. It's just our hand is a little shakier in that right diagram. Okay, now, in terms of efficiency, there is a related property known as consistency of an estimator. And if an estimator is consistent, what this means is essentially that the error or the standard deviation, the sampling error of that estimate tends to converge to zero, tends to get smaller as the sample size gets larger. And what that implies here is that if an estimator is consistent, the actual estimator converges to the value in the population that we're trying to guess, provided the sample size gets large. Okay? So if we get a smaller sample size, we have a lot more uncertainty. But if we increase that sample size, you'll see that the sampling distribution tends to get tighter around that population parameter by which we're trying to estimate. So the idea of consistency here is really that as n goes up, the standard error, the standard deviation under that sampling distribution for our estimator gets smaller. As n goes up, the standard error gets smaller. Now, What is the standard error? Standard error is just a fancy word for the standard deviation of the sampling distribution. Okay. What that means here is if you have samples of different sizes and they have the same, they're drawn from the same population, okay, they could yield different sample means. We saw that, right? There is some sampling error here. The standard error is essentially a measure of that variability from the mean as we move from sample to sample here. It's the variability in the mean as we move from sample to sample. So this is really capturing, to some extent, some sampling noise. Okay? And the way we will define the standard error here, it's related to the population standard deviation. It's actually the population standard deviation divided by a factor, square root n. Okay, and you'll notice here, and you can see it better in this diagram, but as square root n, or rather as n, gets very, very big, okay, what happens to the standard error term here? Well, as n gets larger, that denominator is going up, and it's making the whole fraction get smaller, which is why, as n gets larger, that standard error approaches 0 asymptotically. As n goes to infinity, that standard error declines towards 0 at a diminishing rate. But this is what we mean by consistency here. Okay, this is the property of consistency. As n gets big, the standard error in our estimate gets smaller. So as n gets very large, okay, we're getting a much more reliable parameter estimate in terms of the true population parameter being estimated. So we're going to pick up in the next segment and talk a little bit about the central limit theorem and how to apply Z transformations under the sampling distribution. Stay tuned.